Okay, so I am all wired up beyond the usual, definitely. So I hope you can all hear me everywhere. I'm going to talk today about situated language understanding with visual observations. I usually like to take questions throughout the talk. I am not very religious about finishing my slides, and I prefer to have talks more interactive. This is a fairly technical talk, so we can, and I think that the crowd here is pretty diverse, so we can take it as slow as you want it and kind of like ask a lot of questions. I'm completely okay with that. I'm going to apologize in advance. I have a very bad cough, so I'm probably going to cough multiple times, and with this, it's going to be amplified. Okay, so the long-term goal of what we are going to talk about today is building computing interfaces. It's building natural language interface to computing machines and robotic systems. And you can think about all these different agents that are slowly starting to become more and more common in our daily life. We have all these robotic systems that are much more researchy, these virtual systems. I don't know if anyone here remembers Second Life at this point. And these virtual assistants are becoming more and more common. And mostly what I want to talk about today is focusing on building natural language interface to these systems. Now, except the next slide, there are not going to be any real robots yet. So at this point, it's all working in simulations. But the goal and the assumptions that the research makes are really tied to these kind of scenarios. And I want to motivate why I think that studying natural language within this kind of embodied environment is really important for language understanding. So this is a very small example of our algorithm on a PR2 robot a few years ago. This is a programming by demonstration scenario where my younger self is manipulating the robot's arm and giving it speech commands, trying to teach it some new skills. So what you see here at the top is the robot's point of view from this Kinect camera at the top there. And here is some kind of like a representation of what the robot is learning. And as you will notice, when I give the robot commands, I don't specifically say what arm or gripper I'm referring to. So when I say close, the robot is able to disambiguate here. In this case, means that, understand I mean closing the left gripper. As the interaction continues, and I'll say close again, the robot will again try to disambiguate. And in this case, I understand that I mean closing the right gripper. So this is a very simple scenario. The language here is as simple as it gets. But the reason I'm showing it to you is because it's really a nice illustration of how to understand the language. You really have to take into account what happens in the world. And what the robot takes into account here is the action that it can do, and specifically what the user has most recently manipulated, which is more likely then, and this means that the user is most likely to refer to this object. Okay, so solving this problem or anything more than this very tiny example requires solving a lot of challenges. So we have to solve the natural language understanding problem, which is pretty challenging. We have to solve a lot of vision and perception problems. So the robot has to perceive the environment, understand what objects are there, what the relations between them. And then we have to do joint reasoning about these two inputs to understand what goals the agent has to achieve in order to complete its goal, in order to complete the task. And then do all this like planning and control, solve all these planning and control problems, all these robotic problems that require us to actually generate these actions at a relatively low level to control actuators. Now the way this is done usually in the natural language processing community and also in the robotics community we'll think about it as like computer scientists think about problems. If we have a very complex problem, we'll break it apart into many little problems, and then we'll solve each of them and kind of combine everything together into a system that does what we want. And this really fits something called semantic parsing in language, where the goal is to take sentences and use some kind of a parser, and there are various machines to do this thing, to recover a symbolic form of representation. So this is a lambda calculus expression, but it can be a SQL representation, it can be a small program. And then we take this representation and we mix it with everything else that we understand about the environment, like maybe a semantic map for perception. We'll do planning and control to evaluate the logical form in order to generate the sequence of actions that the agent actually performs. And this approach has a number of advantages and a number of disadvantages. So as far as advantages, it's interpretable. we can actually see, well, if you're an expert in this kind of representations, you can read these representations and see exactly what the agent is understanding. These systems are relatively easy to initialize, and you'll have to take my word for it. I'm not going to talk about it much today. We can define, for example, the meaning of words, so the alignment between specific words and these small chunks of formal meaning. And it's very easy to incorporate expert knowledge, especially in how you design these logical representations. But this approach also has some fundamental problems. So first of all, it relies on building all these different models, often training them, so you need training data, and then combining them all together. And it relies on building and designing this representation. And this knowledge engineering process, knowledge representation process, where you have to kind of like engineer and decide how this formal representation looks like, is very difficult. It tends to introduce limiting assumptions, and it's very, very hard to scale to any realistic task. So what I'm going to talk about today is an alternative approach. So instead of thinking like a computer scientist and doing good computer science, and abstracting everything and decomposing the problem, we're going to think about the problem in one big model that just does everything. So we're going to take whatever the agent observes from the environment, the raw observations, and the text of the instruction. We're going to shove it into a model and directly output actions that the agent has to perform in order to complete the task. And not surprisingly, I'm sure you have seen it in a lot of the meetups recently, we are going to do it with a neural network model. And this neural network model is going to take raw visual input, so RGB pixels. It's going to be trained with a few sample learning regime that explores the environment, but also is able to exploit training data. So we are going to do this in a block world environment, where we are interpreting and executing instructions like put the Toyota block in the same row as the SRI block in the first open space to the right of the SRI block. So what do we have to do here? We have to take, this is our Toyota block, we have to take it, and we have to take it around obstructing blocks, and we have to bring it to this place. Now this red marker is something that we're going to see over and over in the talk. This is only to aid us in kind of like finding position. The agent actually never sees it. So in this case, this Toyota block, we have to take it, we have to go around obstructing blocks and move it all the way until we reach the goal. So what is this domain? So in this domain, we have 20 blocks that are spread over a plane. Each block can be moved in 4 directions. And this means that we have a total of 81 actions that the agent can perform at each point. And this includes a stop action. So when the agent completes the instruction, it must indicate that it completed the instruction. And these blocks, here we see them decorated with logos. Later on, we'll see with logos of companies. Later on, we'll see them decorated with digits. So they can either have one of these 2 decorations. Now, this domain simplifies some problems and complicates some others. So it's a very simple recognition problem for existing vision algorithms to recognize these blocks. It's a very easy problem. And this environment is fully observable. So you never have this problem of partial observability. Memory is not really a problem here. However, there is a combinatorial explosion in the number of space. So all these different configurations of the block are going to they're going to create this very large state of space that the agent can observe, and the agent has to be able to reason about. And the fact that we can have all these blocks in different directions will show up in the instructions with a lot of compositional reasoning. And yes?
Sorry, is this just an example of what you're about to show with the robots in your case, or was this?
This is a domain. So I said there is no robots except the one that we saw.
Yeah. So like, you can of course imagine a case in which, with these sorts of motions, like say the Toyota block is totally isolated, grounded or something.
Yeah.
And so that's part of this problem solving.
So if the Toyota block is completely isolated surrounded by other blocks, and it has to move to somewhere outside the circle, then what the agent should do, I don't think that our agent can do this, is move the other blocks, move other Toyota blocks, and move the other blocks back. So it has to have this kind of, and as far as action space, it can do that, but I don't think that the agent that we learned is able to do this kind of reasoning. Yeah. So when I talk about compositional reasoning, I'm using the term compositionality here like it's used in linguistics, where when you look at these expressions, you see a lot of hierarchical structure in the language. So you have the Toyota block that is in the same row as the SRI block. So you see this very nested structure in the language. In order to understand these instructions, you really have to combine all these pieces of the language together to get the meaning of the sentence. Okay, so how does this compare to some of the domains that have been studied in the semantic parsing literature? So one of the most commonly studied domains and probably the hardest is this SAIL dataset. So in SAIL, what you do is you move around an environment in a maze, and you have to navigate between different places. So the blocks environment that we are going to look at are in most senses, they're actually significantly more difficult. So the sentences that we are going to see are, the instructions are twice the length. The trajectories, the number of steps that we have to do in order to complete a task, these are 5 times the length. The vocabulary is 3 times the size. And the number of states, where here the agent can observe a total of only 400 states. In this case, it's a very large state space. Now, luckily for us, we are going to have also significantly much more data. So here we had around 3,000 instructions. In the blocks environment, we have about 5 times the amount of data. Now, this number here is still going to be relatively small, especially when you start thinking about common solutions to this kind of embodied agents problems that are using reinforcement learning. Okay, so our goal here is to generate a sequence of actions that are required to complete a task. So we want to take the Toyota block, and we want to move it all the way to its goal. So we have to do all the actions. And the setup that we are going to use is motivated by robotics. So we are going to make certain things difficult and not use certain kind of solutions. So one thing we are not going to allow is we're not going to allow any form of beam search. So beam search is this, I hope most of you are familiar with it. It's basically a way to kind of like you can think about if you would do it for a robot, you would have to split the robot and start searching different trajectories, or either go back and forth significantly and rolling back actions. Another thing we're not going to do is we're not going to allow any search procedure with broad exploration. So for example, A-star search can potentially solve this problem relatively easily, but it requires you to explore a large number of space. Again, something that is very difficult to do with the physical agent. What we are going to assume, and this is a common assumption in robotics, is we are going to assume that we can instrument the training environment. So what does this mean? This means that while our agent during testing is only going to observe the environment, the raw visual observations, during training time, we are going to assume that we actually have access to the state of the world. So we know exactly where each block is. So the input that the agent is going to observe is the RGB input from this position. And so this is the kind of image that the agent observes without the red marker. And this is different from previous approaches. So usually what people do in these problems is they either have, they assume that the perception problem is solved and they get a nice structured representation. Or if they are solving the full problem, they are connecting all these models together and that are trained together, and then they are putting them together with some kind of like intermediate representation. So what do we need to do in order to solve, what kind of reasoning is required to solve this kind of example instruction in this kind of state? So one thing we need to understand is we need to understand what block we want to move and roughly where it is in the environment. We also need to understand there is another block mentioned here, the SRI block, but it's mentioned in a different role. It's mentioned in this role that it's some kind of a reference block. We're going to define some position based on this anchor. So SRI is this position anchor. And then once we have SRI, we need to look and compose these larger structures. So in the same row as the SRI block is this band of positions that are across the board, where in the first open space to the right of the SRI block is this position here, and this is the goal position that we have to go to. And then, once we have all this reasoning, what we need to do is we need to generate these actions, or this sequence of actions that take us, in this case, around obstructions, all the way to the goal. Yes? So I didn't say what model we're going to use. So you can think about different models. I mean, semantic parsing, what you do is you define the logic. When you define the logic, you would do exactly this. You define what kind of concept, left off, right off, above, and then you can build these small programs that are actually composing all these concepts into describing a path or a target position. So this would be a semantic parsing approach. We're going to do this with a neural network model, like I said earlier. And this neural network is it's going to be a very simple model. So our model creates a representation from the images that it observes of the environment. It creates a representation of text, and then it combines together to decide what action to take. So to process the observed images, we concatenate several images to give the agent some kind of idea of history. So the agent sees previous images. For those familiar, we concatenate it along the channel dimension and put it through a convolutional neural network to get an embedded representation of the visual state. For the language, we do something very simple. We just put it through a long, short-term recurrent neural network to get a representation of the instruction. We then concatenate these two vectors together and add an embedding of the previous action the agent performed. So again, we want to give the agent some kind of an idea of what it has done before. We take this representation that represents the kind of the state of the agent right now, and we put it through a multi-layer perceptron that is decomposed according to the action space. So what do we need to decide here? We need to decide which block we want to move. So we have this softmax over all the 20 blocks that can be in the environment. And we need to decide what direction we want to move. So it's another softmax. And then the probability distribution, the probability of an action is the product of these two probability distributions. So in this case, we're deciding to move the Toyota block and moving one step south. So this model defines our policy. And what this policy is going to take something called the agent context. And the agent context is distinguished from the state of the world. Whereas the state of the world is actually where each object is placed in the environment, the agent context doesn't have access to this information. It takes the instruction, it takes this sequence of images that I mentioned, and it's going to take the previous action. And it's going to use this information to decide what action to perform. The agent will perform an action, it will observe the new state of the environment, the agent context will update, and the agent will get the next action. And it's going to continue this until it generates a stop action, and then an instruction is complete. Yes?
In the task-specific layer, what ensures that the directionality and the tracer block are actually linked to one another? If you have two separate softmaxes, how do you know that you're not going south on the wrong block or
so
the right direction in the wrong block?
Okay, so what do you mean the right direction of the wrong block? So you have this representation here, this initial layer of the perceptron is actually joint for both of them. So there is some kind of grounding happening there. But these things are independent. So you can actually get a situation and you can guess actions that are impossible. So for example, if you have the Toyota block is at the edge of the screen and you might guess to try to move it south. And nothing is going to happen because it's reached the border of the environment. And this can happen. Nothing guarantees that it doesn't. The system will try to learn not to do this.
Why do you need the previous images?
Okay, so this is a great question. So some instructions, they require you to understand what's happened. They benefit from understanding what's happened before. So previous images, for example, will tell you that you have been moving straight for a while, or maybe you're actually moving in a curve because you can see different position of the object. And this can help you reason about where you are in the instruction.
So you found that it performs better with?
So I don't have numbers for ablating the images. I have numbers for ablating the previous action, and the performance drops a bit. So there is some kind of temporal reasoning happening here. In more current, so this is a very simple model. In more sophisticated model, you actually have you're doing a recurrence over the entire execution, which incorporates these things in a much more heavier way with even more parameters.
So the input to the CNN is 9 deep, is that right?
It's actually 12. It's actually 12 deep, yeah, because we actually use 4 images in practice. So here I just put free. It's a hyperparameter. But yeah, for each image, you have a free channels for the colors. Yeah. Yeah.
What is the input to LSTM? Because like, I see just for seeing them, the image processing.
Yeah.
For LSTM, what would be
the tokens of the instruction. So you're going to process the instruction in the order of the tokens. So the first input is embedding of the word place. The second input is embedding of the word there. The third input, and that's the recurrence. Now these embeddings are going to be learned from the system. We are not using pre-learned embeddings for this. So everything that you see here, all the parameters are going to be learned from scratch. In that sense. Yeah.
So for me as opposed to like the semantic parsing approach, this still kind of seems like a little bit like it's semantically parsed, just that each operation is some form of a neural processor. Is there another step that we could go that would really be something that was a direct mapping where you just have inputs on one end and output on the other end, and there's not expert knowledge going into the structure of the network that would decide what the output would be and make it run the correct operation? Am I misinterpreting that?
I think so. A semantic parsing approach would have recovered a logical form that captures this, and then this logical form would be executed. This logical form would have, you can think about it as like some kind of an expression tree with conjunctions, disjunctions, negations, number of predicates that are testing different conditions. This is the same network regardless of the instruction. So it's a constant network. Now, am I going to design this like fully connected neural network that I just throw and everything works at? Well, you know what? Maybe, but every paper that is working on neural networks in the last 5 years seems to indicate otherwise. So you can think about convolutional neural network, for example. They're a very specialized neural network that incorporate a lot of expert knowledge. So they are already not fully connected layers. And recurrent networks, they're doing the same thing. They're kind of taking into account the fact that words have a very specific ordering, and sentences can come in various lengths. You know, how would I have, if I just have a feed-forward network, dealing with inputs that are coming that are of varying lengths is going to be either difficult or just wasteful. Yeah.
Do you think that by averaging the word embeddings to the instruction representation, you're losing some of the order of the operation?
Yeah, so potentially, I don't think it shows in this domain. I don't think the instructions in this domain have this what you're looking for, because I think you will see this happening when you have some kind of like intermediate goals that you want to achieve. This doesn't happen in this domain, but yeah, this is an insanely simplified representation of text. Yeah.
Would having LSTM on the previous actions rather than one action be helpful in this case?
Potentially. We didn't try that. So what we learned is like, and that's what kind of like ended up with this relatively simple network, is that these networks are really hard to train. And especially when you have some kind of like a agent that learns for interaction in the environment, in some kind of a style of reinforcement learning. More complex networks that at least conceptually should perform better don't always deliver. It's very hard for them to learn to assign the blame and the credit to the right part of the network.
Because you try to assume that some level of previous attempt is encoded in the CNN here, right?
Yeah, but this is only this is only the last 4 actions. So some of the, I'm not going to talk about it today, but some of the models that we are currently working in actually have unlimited horizon, so they run an RNN over the entire thing. But they require some hand-holding to train them right. So the more, when we started this, we actually had more sophisticated idea of how we're going to try things and architectures that are more interesting. But what we learned is that it's actually very hard to train these things in order to make them behave the way you want. And the more you have more parameters and where things to go, you can overfit in more and more bizarre ways and not generalize.
When you connect the CNN to the output of the LSTM, are you like updating the weights on the other parts of this, or are you literally just like freezing the weights
So the loss that we are going to have is going to come from here and propagate all the way to the network. So we are going to, sorry? All the way through. For every action, we're going to have a loss coming through here and going to update all the weights. Yeah. Okay, so the advantages of this model, the big advantage is that we don't have these immediate representations, so we don't need to design these logical representations, which in practice are actually very difficult to design, and I can testify that having done this for quite a few years. This model does not require any planning procedures, and it doesn't require us to take all these different models, build them, train them, and connect them together. However, nothing comes for free. What we did is we traded off this engineering effort and this knowledge representation effort with a learning problem. And now, where we could initialize the system and have all our expert knowledge, now we have a much more flexible system, but also a system that is much harder to initialize and much harder to kind of like to learn, and that requires significantly more data. So what's the learning problem here? The learning problem that we are going to have is we're going to have training data where we have instructions paired with demonstrations. And this means that, let's say, this is our example instruction, the one we looked earlier. What does this instruction do? It takes us from this start state to this goal state. What we are going to have access to is all the intermediate action and state that are required to execute this sequence. So in this case, this is like something like 35, I think, of different actions that are required here. Sorry, 34. So we can do something very simple. We can, the most simplest thing to do as far as learning, and it's a good starting point, it's actually perform better than you would expect, is try supervised learning. So how do you do supervised learning with this data? You just take this data and you create these tuples of instruction, state, and the action. So basically you have this classification problem, and you can just train it with a maximum likelihood. So it's a very simple approach. It's very easy to build, and it trains really, really fast. The problem here is that we actually have very limited data compared to the kind of reasoning that we require the system to do. And even a bigger problem is this data is really biased. So this data is only observing state-action pairs along this like very neat execution of the goal trajectory. But here, the large action space and the complex reasoning, this makes it's very likely that the agent during testing will just kind of like deviate from the right trajectory, and then it's in a no man's land. It's in a part of the state space. It's never observed during training, so it's not going to recover. So what we need to do is we need to observe more data to kind of like to feed our network. And we need to observe more data that is beyond this like gold pristine trajectories. And this, of course, connects very nicely to all these ideas in reinforcement learning, where you are learning through interacting with the environment and getting rewards. So our goal is to learn an agent that, giving an instruction and image, selects the next action. And this is very similar to reinforcement learning. There are some differences that are coming from this domain. So this is a very classical reinforcement learning problem. What we do during training is we play Super Mario and we get rewards. What we do during testing is we take out the reward and we let Super Mario keep playing, and we see it outperform humans or whatever, and works pretty well. So this is a video that I got from this GitHub repo. Our scenario is a bit different. So whereas here you're trying to learn a behavior, and the agent that learns the behavior will then execute this behavior, here we're trying to learn to execute tasks. And these tasks, we're going to have a very large set of tasks during training, and we're going to have a very large set of unseen tasks during testing, and these tasks are decoded in this weird thing that is called natural language. So getting this kind of learning algorithms to work in this scenario requires solving three major challenges. The first challenge is how are we going to kind of like learn from all these different tasks? So actually what's happening during training, we're going to see these many different behaviors depending on the instruction that we are getting. So we need to generalize across them and learn to, so we need to learn across all these different instructions and then generalize to be able to execute new tasks. We also need to be able to take better advantage of our training data. So in reinforcement learning, usually what you do is you just kind of explore the environment, and if you complete the task, you get a reward. But in instructional language, it's very natural to get demonstrations of the desired system behavior, because this is not just an agent that runs forever and ever. This is a very finite, well-defined task. You can actually ask humans to perform it. So what we want to do is we want to leverage these demonstrations, and we're going to do it using something called reward shaping. And finally, reinforcement learning is notoriously data hungry, but the natural language data that we have is very limited. So what we're going to do is we're going to break a lot of the reinforcement learning assumption and use a learning algorithm that is able to learn with relatively small number of samples. Sorry. Okay, so to learn from any task, we're going to do something very simple. We are going to define the reward for every task. So for every sample that we have, we define a different reward. This reward is going to take the state, and it's going to take the action, and this is where this ability to instrument the state during training kicks in. The agent's going to get a very large reward if it completes the task and gets it done well, and it's going to get a very negative reward if it says I'm done, but it's at the wrong place, or if it's lying, or if it's doing something very stupid, like trying to do an action that is impossible, like going off the edge of the board, for example. And otherwise, we're going to give it this small verbosity penalty. So for every action, it's going to get this small penalty that will encourage it to be more efficient. So what this reward tells us, it's basically, I don't care how you complete the task. You should complete the task, and you should do it relatively efficiently, and don't do anything stupid along the way. So it doesn't really dictate exactly how the agent should behave, but it gives us very roughly what an ideal agent would look like. And the objective that we define is this policy gradient objective. So whereas in a policy gradient in reinforcement, usually you have a single value function, we have a value function for each possible example, so we average across all these value functions. And our reward in practice, for those not familiar with the value function, it's incorporated inside this term here. Okay, so how well is this going to work if we just start now? Yeah.
So N here is all of the.
N here is the number of instructions you have in your training data. So this is iterating over the tasks in your training data. Each task is an instruction, so with a start state and a goal state. That's your annotation. So how well is this going to work when we just started? So when we are starting these neural networks, we don't really know how to initialize them in any very informative way. So what's going to happen is something like this. The agent is just going to do random things. And this is going to make our life very difficult. It's actually going to make learning completely impossible. Why is that? It's going to make learning impossible because we are never going to observe any positive reward here. There is no chance in practice that we will get all the actions that are required, these 35 actions we saw earlier, to get to the goal. What we'll have to do is we'll have to pick the object we want to move only that, avoid moving everything else, and get all the way to the goal. And this is just in practice never going to happen. The agent is not going to observe any positive reward, and it's just going to get stuck. In some cases, what it's going to learn that it shouldn't even try anything, and it's just going to say, I'm done, even before trying anything. Okay, so what we need to do is we need to put something in our reward that will make it more informative. Our reward right now is very sparse. You only get a positive reward at the end. So we need to have more information there. And the way we're going to do it is something called reward shaping. Reward shaping is a way to add just additive terms to the reward. And we're adding two terms. One that will allow us to incorporate information about the distance to the goal, and one that will allow us to incorporate information about following demonstration. And the way we do it is using something called potential-based shaping. So potential-based shaping is this really nice way to add information into the reward while actually not changing the order of policies. So the final reward that the agent gets at the end of the execution remains the same. And the way you do it is you define a potential, just a simple function that giving a state and action pair for any state action returns a number. And now the shaping term defines the difference between these potentials. So I reach state S prime with action A prime, and now what I'm doing currently is I'm taking action A to get to state S. So the shaping term that I will add to my reward is the difference between the potentials that I had. And for those more familiar with how reinforcement learning works, when you're maximizing the total expected reward, what you're going to get when you sum the total rewards along your execution is you're going to get this like telescopic collapse. So these terms are going to cancel each other, and in practice you will see no difference in the order of policies. So you're not changing the problem. You're still learning a policy that is optimal under the original reward of the problem. And if you're interested, these are the papers that actually prove it formally. Okay, so the first shaping term we add is going to reward the agent for getting closer to the goal. And the way we do this is we define a potential function, which is the negative distance from the goal state. So if we have two states, so we have all the configurations of the blocks in the environment, we measure the distance between them as the sum of the Euclidean distance between each blocks, depending on how their location is. Now, so if the agent moves closer to the goal, it's going to, this shaping term is going to be positive. So it's going to push the reward up. If the agent moves further from the goal, this shaping term is going to be negative. So it's going to push the reward down. And we can actually visualize it under some very restrictive assumptions. So if we assume that we can only move one block, we know what block we are moving, we have a much more limited action space, we can do a two-dimensional heat map. So this is the problem reward potential. This is only the positive part of the problem reward. And what we see here is that basically there are no values anywhere else except the goal where you have this really high potential. Now, this distance term potential gives us a much more dense environment. So now we have a different value for every place in the state space because we can compute the distance to the goal. So you can think about it as what we did here is we created this mountain, and the peak of the mountain is at the goal, and the agent wants to maximize its altitude. So it wants to reach the top of the mountain. And at every point, the potential is the current altitude of the agent. So if it moves up the mountain, it's going to improve its altitude, and the difference between the potentials is going to be positive. Now, this is going to help us a lot. Now we got rid of the sparsity problem here. But what we still have a problem is that a lot of the time, actually, we have to go over obstructing blocks. So what we need to do is we actually need to go down the mountain before we can climb up. And this reward, in this shaping term, is going to actually decrease the rewards for that. So it's going to penalize for this behavior. So if we are going here now, we'll get negative reward because of this shaping term, and which basically will persist until roughly here when we start climbing up again. So what takes care of that is a second shaping term, and here is where the demonstration kicks in. So remember, we're talking about instructions. It's relatively easy to get demonstrations. So this shaping term, what it's going to do, it's going to reward the agent for roughly following what the demonstration does. So how do we define it? We are going, this potential now is going to be a positive constant if the state where the agent is right now is relatively close. It's similar to one of the states along the demonstration. So we're going to have some kind of a threshold on the distance. And the agent is taking exactly the same action. So we're not going to require the agent exactly to follow demonstration. You can think about it, we are creating some kind of like a margin around demonstration where the agent can be. As long as it's moving in the right direction, it's going to get, this potential is going to be a bit positive. So if the agent approximately follows demonstrations, this potential is going to be larger or negative, larger than 0 or equal to 0. And if it's not following demonstrations, this potential term is going to penalize and take the reward down. So we can visualize this just like we did before. This is our problem reward potential that we saw earlier, and this is the similar visualization for what we get from demonstrations. So what we see here, so this is in blue, this is our demonstration. We see this really strong potential along this demonstration. Everywhere else, we see nothing. It's a desert again. So the problem in this, so the problem of using only this shaping term is that all that we see around here is actually, again, we have this sparsity problem. The minute our agent goes a bit off the golden path, it's not going to see any informative reward. So the natural, yeah.
But if the agent somehow were to, I guess early on, especially somewhat accidentally, or have a new successful trajectory, so you had some measure of being almost as good as a demonstration, could it incorporate that in the demonstration, or it's only using the training data?
So it's only using the training data, but you have this is a great point. So there actually we have one trajectory, but there are many possible trajectories. And something that is interesting to think about is what happens if you actually have access to this kind of data. It's very easy to incorporate multiple trajectories in this demonstration term. You just find which one you're the closest to, and this is the one that you're using. But the data that we don't have that. So it's an interesting question. Okay, so what happens when so the natural thing is to combine these two things, and what you get is this very dense potential. Now you have potential across the entire state space, and you can think about it again as a mountain, and what you have here along the demonstration is this very high ridge. So if you want to maximize your altitude, you just stick to the ridge, and the ridge goes up the mountain. Okay. So we beefed up the reward with much more information. We have a much more dense reward. The last problem we have to solve is the fact that reinforcement learning is extremely data hungry. And in practice, is not going to work on this problem, and I'll show the results later. Now, our problem is, and that's where things start to become very different from some of these, the successes that we see in Atari, for example, is that we have very limited language. We can play with the simulator forever, but the language that we are going to observe is only going to be the amount of language, the sentences we have in the training data. In this case, something like 11,000 sentences. We are never going to see any new language, and that's relatively limited. So what we need to do is we need to learn with much more limited data, and to do this, we break a lot of the reinforcement learning nice assumptions, and we want to pretend that what we have is a contextual bandit problem. Now, what does it mean that we have a contextual bandit problem? Very simple. It means that we are going to start maximizing the immediate reward rather than the total expected reward. And this has some very nice theoretical advantages. There is a very nice theoretical work from John Langsford's group and from this paper from Krishnamurti in 2016 that shows that optimizing the immediate reward is actually much easier than optimizing a total expected reward, and you get much nicer upper bounds on sample complexity. What it means for our gradient, so this is our gradient. If we were maximizing a total expected reward, this would be our Q function that includes the total expected reward. Now we are using the immediate reward here. This is the only difference. It's just a tiny difference in the objective. Of course, nothing ever comes for free. So remember that very nice guarantee we had because we used this potential-based shaping. So that's out of the window. It actually doesn't exist for contextual bandit. There is no theory behind it. And there is also no theoretical guarantees for the optimal policy. Although arguably this doesn't exist in recent years, in recent works as well, because we are working with the non-convex functions. But and this is what we're going to see in the result, it works really well in practice. So we did three things. So we modified our objective a bit to incorporate all these different tasks by defining different reward functions from them. We leveraged demonstration using reward shaping, and we learn in a few sample regimes by switching from reinforcement learning to a contextual bandit problem. Okay, so there is a lot of related work. I'm not going to go over this slide. There is a lot of, in much detail, there is a lot of work on instruction execution with kind of like decomposing the problem and using structured environment. There is a lot of work on language and vision in the last few years. There is a lot of work on using neural network function approximators as policies in reinforcement learning. And the most related work potentially to our work is this work that's actually coming from robotics, where people are using reinforcement learning to learn neural network functions to do control. Okay, so for our evaluation, what we are evaluating is task completion. So we are evaluating, and we're evaluating how good the agent was able to complete the task, and we're going to compute an error measure. And this error measure is the distance between the states. So if we have the goal state and we have our final state, we're going to look at the distance between each pair of blocks, and we're going to sum these Euclidean distances. So here we have the Toyota block is not really in place, this block is not really in place, and the SRI block is not really in place. We're going to sum these distances, and this is our error. For experimental setup, we use the train dev test plate that came with this data originally. We regularize with an entropy term, and this is extremely important, and we compute the gradient with sampling, and we initialize this whole thing with supervised learning, and we're going to see some kind of interesting trade-off that this allows us to do later on when we analyze the results. Okay, so I'm going to start with our final test results, and then I'm going to start looking at examples, and I think that's where the more interesting bits are. So we are comparing here to two non-learning baselines. So what happens when you just stop? You get an error of 6.2. So this is not doing anything. What happens when you just start moving things randomly? The action space is very large. You can do a lot of stupid things. You get a very large error. Supervised learning works pretty well. It gives you an error of 5. So a significant improvement over not doing anything. We compare it to two reinforcement learning baselines. So reinforced that uses policy gradient, and DQN that uses Q learning. Both cases, the reward function is the shaped reward function using both shaping terms. In the case of reinforced, we're also using supervised initialization. In the case of DQN, it's less obvious how to incorporate supervised initialization when your model is not probabilistic, so we're not using it. So and this is our approach. So we see a significant improvement over the other baselines. The only difference between this reinforced model and our approach is using this contextual bandit setting. So it's this approximation that happens in the gradient of using the immediate reward rather than the total expected reward. Otherwise, these models have access to exactly the same information. Okay, so I want to look at some examples. I'm going to start with cherry-picked examples because they just look nice. But then I'm going to move to some errors. And I think that's where it's more interesting to see where the system failed. It kind of exposes some very interesting open problems. Okay, so this is the first cherry-picked examples. You want to move the target block up 2 block lengths, move the target block right until it is under the stellar blocks. By the way, the target blocks is the one with the target logo. So this is supervised model. This is the policy gradient reinforced model, and this is our approach. Supervised model is doing pretty well here. It actually gets it very close to getting it absolutely right. The reinforced model just gets stuck in this oscillation. It's something that we actually see very common. And our approach, where it's a cherry-picked example, so it's going to do very well. Another example, so here we have to take this Mercedes thing and move it to the marker here. We have to follow this instruction. Supervised approach is doing very bad in this case, just going in the other direction for some reason. DQN just gives up and doesn't do anything. And our approach, again, performs relatively well in this scenario. Now, I'm going to start from a minor example, and I'm going to slowly escalate to from a minor failure, I'm going to slowly escalate to worse and worse scenarios. So this is a small failure. Here, what you need to do is you need to take this HP block and you need to move it to here. So what do? The agent moves the HP block, gets it to the right position, and then kind of moves away a bit. And this is a small example of a failure that is actually very common. And here you can see it much more pronounced. So here we want to take the 18 block, and we want to move it roughly to here. So what does the agent do? The agent moves in the right direction, gets to the goal, moves out. Gets to the goal, moves out. Gets to the goal, moves out, and then we stop it because we reach the maximum number of steps we allow it to take. And this really illustrates a problem that is actually very common. The agent is very bad at stopping at the right place, or at even stopping at all. And we can quantify it. We can ask, what will happen if we stop it at the oracle position, the closest position it ever reached to the goal? And when we do this, we actually see significant improvement across all the baselines. So this is the problem that all the learning systems have to figure out how to execute the stop action. And so, okay, so one question if you ask yourself, okay, so maybe it's an overfitting problem. How much of it is overfitting? Maybe we can actually stop perfectly on the training data. And again, we can measure this. We can look stopping, we can roll out, do inference on development and training, and we can ask how many times we exhaust the maximum number of steps, how many times we actually have to stop it. It never actually stops. So in development, it's 55% of the time we actually have to stop the agent, to kill it, where in training, it happens less, but it still happens significant number of times. This is 30% of the time. And the number of the maximum number of actions that we allow is actually above the maximum number of actions that exist in the training data. And we can also look at how many actions on average the agent takes. So for development and training, the gold examples have roughly 15 actions. So roughly the same length of trajectories on average in these two splits of the data. For development, the agent on average takes almost 29 actions, significantly more than it needs. And for training, while the situation is much better, it takes on average almost 22 actions. So we do have an overfitting problem here, but we actually have a serious problem of still, even on the training data, it doesn't know when to stop. Okay, so why am I going over and over and talking about this one stopping action, and why do I think it's so important? So I think stopping is actually a very important problem. And you can think of, like, you have this agent, you give it instructions like your car, you want to see the sunset, so you want to go slightly closer to the cliff. You really want your agent to stop at the right position. Now, surprisingly, when you look at work in reinforcement learning, this is a problem that is extremely understudied. Usually what happens in reinforcement learning is the agent gets into a certain position, which is the goal position, and the world stops. The simulators or the environment just stop, and the agent never actually has to understand that it completed a task. It just has to kind of like step on the button. Okay. Yeah. This is a, think about it. When you're next time you take the JFK air train, which is automated. When does this stop? It will stop in a second. Yeah.
Is there a way for you to assign more weight to actions that occur when you're closer to the goal?
Yeah, so we tried that. It didn't really help for some reason. I'm not really sure why.
It almost seems like it's looking at the sentence and it's like, I need to do X, Y, and Z, and all actions are treated equally.
Mm-hmm.
It's like, go up and go to the right. And it's like, I'm happy going up and going to the right. And then it resets and goes up and to the right again. But it doesn't understand that the ultimate goal is more important than the up and to the right part.
Yeah, so we tried to, I'm going to stop this. So we tried to kind of like to change the learning algorithm to expose it to more suffixes of actions, and for some reason it didn't help. We actually have a new learning algorithm that requires various assumptions about how you observe rewards, but it's able to overcome this problem. And so that brought us to the hypothesis that what's happening here is mainly an exploration problem. So, and I don't have that one is in submission, so I'm not going to talk about it, but you can think about it like this. Your agent is going to start doing actions. Now, the things that it's going to learn how to do first are the actions at the beginning of that it has to do at the beginning, because that's, it's going to get the reward. It's not at the end, so it's not going to learn how to do these things. And then now so what never happens in the beginning. It never stops in the beginning. It's going to develop a really strong bias against stopping. Now, your exploration is based on what your agent knows. So you're going to sample from your policy new actions. Now, if you learn a very strong bias against stopping, you're never going to sample it again. So you're very unlikely to explore stopping. Now, stopping is even harder because you can't explore stopping in different places. You have to explore stopping in exactly the right position. And that's going to make learning it very difficult, especially after early doing learning, you learn these really strong biases against it.
So adding a term that says you're within 2 blocks distance of the stopping goal doesn't help at all?
So we actually have a margin there. Yeah. So we have a pretty nice margin. If you stop in the margin, you get the reward. But it's still relatively to the size of the environment, it's very difficult. Yeah. Mm-hmm.
With the demonstration path and the distance, it's a very flat potential. Near the target, it's just going to wander around because there's no gradient for it to follow. So if you have a steep gradient, right?
Well, so remember we have the distance term. So it just wanders around. It's going to increase its distance at some point. So it's going to get some positive rewards for these actions that are wandering off the goal. So the reward actually should take care of it. Now, the agent actually never sees a positive reward unless it says stop and it says in the right place. So this final really high positive reward. So the reward should have taken care of it. So we believe it's more of an exploration issue.
Why not increase the penalty for a longer and longer solution, or increase it like exponentially?
Yeah, so there is a trade-off here. So if you increase the penalty, it's going to overshadow other terms in your reward. So the penalty term that we're using, and I don't remember the.
So like in a weighted fashion, so that the greater it gets, but the more steps you take, the more expensive penalty is.
So some instructions do require a larger number of states. So maybe you will say, what, I'm going to adapt it according to the sense of demonstration. It starts to be very complicated. Maybe you can design a very smart reward function with a very smart penalty, but I think it's going to be pretty difficult. Yeah.
I see you've got a language slide here. You haven't talked yet about how the language comes into it, like how it understands what left and slide and all that means.
So the language comes through the LSTM that we had in our neural network. Now, all these things are learned implicitly. So it learns them for exploration, for trying things in the environment.
So how does it know that it just wound up on the right? Just did it try it enough times and it says, well, I guess right is not this, it's that?
So how does it know that right of a certain block means something? It gets rewards for the right interpretations. So it's very hard to see this. And this is if I get to continue, I'll get to this slide. These models do one of the big problems with them is they are highly uninterpretable. So it's very hard to see what they are learning. But implicitly, in order to complete this execution, it has to learn this. And it learns this implicitly. It learns this implicitly by reasoning about certain things it gets from the convolutions, from the embedding of the environment, and how it combines with certain tokens that it sees during in the instruction. Yeah.
So you learn the LSTM together with the reinforcement, right?
So yeah, all the parameters are learned together.
So there are two main, I guess, style of way learning, right? Between LSTM versus reinforcement. So my question really is, because to some degree in your question, is it possible that, let's say, we have LSTM to learn sentence into the goal where the target is, right? As a separate learning. So we learn only from understanding what the goal is. And then we use reinforcement learning to learn how to achieve the goal. In that case, we will go to the right place, verify whether demonstration to the goal or whatever it is, right, with the reinforcement reward. In separation from LSTM, because I think during propagation you start losing some, at some point LSTM, even though you can remember, but if you have longer sentences, you start losing the context.
So if you want to predict the goal with LSTM, you also have to learn the weights of the CNN, right?
Yeah, that's fine. I'm saying
but
two learning problems.
No, but you can't separate them because you have to identify the goal. So you have to identify the place on the image.
So what I would train, let's say, for example, if this works, then I train with the sentences, right? And place, okay, Toyota is supposed to start from here with the CNN, start from here, and go here, right? So I guess.
But how would you separate the CNN training? So most of the weights are in the LSTM and the CNN. The MLP, there's not that many weights there. So how would you separate the CNN training from the LSTM training? I mean, you can think of things. You can do like autoencoding for the CNNs. You can do that, but it's not really clear that it will work better.
Yeah, because I'm guessing that with the reinforcement is kind of diluting the part about CNN that you're learning. I guess I don't know for sure. But let's say if you have an image of like, okay, here's the starting point, here's my LSTM learning, and here's the goal. This guy go there, right? That's it. I'm learning that, and then you separately learn.
But this is most of the network already. This is most of the network already. So you have to learn the CNN and you have to learn the LSTM, And now,
what I'm trying to say is separating reinforcement out of it. That's my gut feeling. I'm not.
so you would do supervised learning, right?
Yeah.
And this doesn't perform as well.
One thing, I don't know if it makes sense, but the supervised learning is a binary classification task, so should I stop or I shouldn't?
Okay, so you can change. So you can actually change. So instead of having this like predicting straight this probability distribution, you can actually do binary prediction of stop or not stop. And if I don't stop, I go and predict the action, right?
Yeah, and if you don't stop, you go through the
Yeah.
reinforcement. And that's, if you look at your results.
Wait, so I'm not sure I understand what does it mean to go through the reinforcement learning approach.
So I mean that for in every position, you just use a supervised model just to tell you if you should stop or continue. If you continue, decide the next task, sorry, the next step based on your original model.
Mm-hmm. So I'm not sure what your objective function will be and what your loss will be. We did try once kind of like training with this kind of like hierarchical decision process. You're first deciding if to stop or not, and then decide, and if not, decide the action. Didn't really change much, because at the end of the day, you're still not unlikely to observe the stop action. Now, supervised learning, we did train with supervised learning, so it actually gets a supervised to a certain extent.
You got 2 classes versus 40, I think, right? Or
81.
81, so it's technically an easier task.
So it is an easier task, but so the reinforcement learning will still propagate weights into the first binary decision, stopping or not stopping, right? And because it will do that, it will do exactly it will do exactly the same problem. It will learn a very strong bias against not stopping. So it's very nice that you have this separate branch, but you will just never take it. Yeah.
Maybe I'm misunderstanding, but didn't you say that you did initialize the weights by first doing supervised learning and then reinforcement learning?
Yes.
So, I mean, did the LSTM weights continue to change much after the supervised learning?
I don't know how much they changed, but we don't fix any of the weights. But I mean, in practice, you know, the fact that from supervised learning you see such a big improvement in performance, I suspect there was a significant change in how the system works. And I can maybe I'll take a few more.
Maybe not on the interpretation of the command, and more on the trajectory planning, right?
I don't. It's very hard to separate between these things, right? I mean, we can hypothesize. Yeah, the language is doing some understanding, and then it learns something that is independent from the planning, and then the planning is happening downstream. But it's actually a very dicey thing to say, because there is no empirical evidence for that. So I want to continue with a few more slides, because I want to talk, because you mentioned supervised learning. So here we're doing a few more analysis. I'll try to do it quick. A few more error analysis here. This is something show about the language. As expected, the more unknown words we have, our performance decreases. This is a very interesting experiment. What we are doing here is we are assuming we have a planner, and now what we're going to do is we're going to predict the goal. So we assume that we are building a planner. We are giving up on like learning the entire problem. What we are doing is we're predicting two things. We're predicting which block to move, and we're predicting what goal we want to move it to. We have the goal position, and this shows significant improvement in performance. It actually shows that there's still a significant planning problem that's kind of like stuck into our learning algorithm. Okay, so I mentioned that we use supervised learning, and there is something very interesting we can do in this algorithm because of how the reward decomposes, is we can vary the amount of supervision we are using. So what does this mean? So if we use less demonstrations, that means that we are removing these demonstrations from the supervised initialization, and we are removing the second shaping term for all these examples from the contextual Bandit learning phase. And we can vary that, and we see that when we have access to roughly 12% of the demonstration, we already get most of the benefit of using them. Now, this example here, this point here is very interesting. What's happening here is you have no demonstration at all. So no supervised initialization and no second shaping term. And indeed, we have very bad performance here. So the learning collapses. Now, what we can do is we can actually see that there's a lot of overlapping effect between the two. So if we don't use any demonstrations, then we get a 5.4 error. But if we use demonstrations only for the second shaping term, but without any supervised initialization, we get actually pretty close to our approach. So it gets 3.78, where if we don't use the second shaping term, but we do use supervised initialization, we get roughly the same result. If we use both of them, we get a further boost, but they actually have a lot of overlapping effect. Okay, so I can show a few more errors. These are more potentially perceptual errors. So the agent is actually very bad at getting itself out of corners. It tends to get stuck. It doesn't know what to do when it's kind of like, possibly for the CNN, it's hard to understand what's going in this very crowded area. And it's also very bad at getting through narrow spaces. So this 5 here is supposed to go either through here or through here to get into this place, but it's actually just, it's very hard for the system to overcome this. And we suspect this is a perceptual problem. Okay, so we can compare this to the semantic parsing approaches. And so in semantic parsing, we have a number of advantages, a number of disadvantages. And in this model, in this approach as well, we have a number of advantages, a number of disadvantages. So it's a single model approach. We train it only from demonstrations. So we don't need training data and much engineering. We don't need to design all these intermediate representations. However, it's completely not interpretable. So people are asking, how do you know that it's learned left off or right off or stuff like that? Well, I don't really have an insight into the network to understand what it learns. I can look empirically and see that, yes, it has to understand these concepts to a certain degree in order to execute the task. But it's actually very hard to understand what it's actually learning and what reasoning it's actually doing. And it's also not really clear how to incorporate a lot of expert knowledge into these things. Okay, so to summarize, so this work was done by my student, Dipendra Misra, in collaboration with John Langford from Microsoft Research. We have a neural network model for mapping instructions to actions, instructions on observations, and we train it using a few sample learning regime using a contextual Bandit. You can actually download these things, and Dipendra prepared this nice instruction sheet. He claims you can run it in 60 seconds if you follow his instructions accurately. Okay, so what I can do now, what I'm going to do now, I'm going to skip the last part of the talk. I was hoping to talk about this really cool data set that we did for vision and language, but I'm going to skip this so I can take a few more minutes for questions. And I hope you guys take a chance to visit our new campus on Roosevelt Island just outside of Manhattan. So thank you very much, and I'm happy to take more questions.